Hello class. So welcome to 5.4 head-on elastic collisions. Our first section says perfectly elastic head-on collisions in one dimension. So first off, what is a head-on collision? Well, this is an impact where two objects approach from opposite directions and momentum and momentum and kinetic energy are conserved. Okay, so that's our head-on elastic collision. So two things coming right at each other, and they end up having momentum and kinetic energy conserved. Great. Now in this sort of a situation, we have some equations that we can use. And this is what I was saying on the previous lesson. These equations make our lives a lot easier. So we have VF1 is equal to, here we go, VF1 equals M1 minus M2 over M1 plus M2 times VI1 plus 2M2 over M1 plus M2 times VI2. There you go. That's our equation for VF1. And you can see in the textbook the full derivation. It's pretty cool how they got there. But yeah, it's really useful. And then we have VF2 is equal to the same basic idea, but you'll see that all our numbers are reversed. So it's the exact same as the previous line, but all the 1's become 2's and all the 2's become 1's. So you'll see it's M2 minus M1 over M1 plus M2. That bottom I could have written it as M2 plus M1 if I wanted, but it's the same thing. Okay, VI2 plus 2M1 over M1 plus M2 times VI1. Okay, so you can see how all the 1's and 2's just switched there. Those are our equations. So if we have two objects, doesn't matter what their mass is, doesn't matter how fast they're going, if they're coming straight at each other, then their ending velocities will have these values. Now there's a special case where if one of the initial speeds is 0, if one of them's starting at rest, in this case we'll say that, let's say number 2 is starting at rest. Well, you can see that, that some things would cancel out. We would have the whole VI1 terms would cancel. So we get, in the end, these simplified equations. VF1 is equal to, so if VI2 is equal to 0, then we just get this first term here, M1 minus M2 over M1 plus M2 times VI1. Okay, and for our VF2, you see in the VF2 equation the whole first term disappears because VI2 is 0. So we get just the second term, 2M1 over M1 plus M2 times VI1 vector. There you go. So that's our special case. Okay, and using these equations we can do some pretty neat physics. Problem 1 here says, consider an elastic head-on collision between two balls of different masses as shown. The mass of ball 1 is 1.2 kilograms and its velocity is 7.2 meters per second west. You can see that's the one on the right in the picture. The mass of ball 2 is 3.6 kilograms and ball 2 is initially at rest. That means we can use our special case formulas. Determine the final velocity of each ball after the collision. Okay, so let's see here. We've got VF1 is equal to M1 minus M2 over M1 plus M2 times VI1. That's all we need to know. So I can plug in some values here. We've got 1.2 minus 3.6 over 1.2 plus 3.6. times negative 7.2. I'm picking east as positive, so it's going 7.2 west. So this comes out to 3.6 meters per second east. And there we go. That's half the problem done. And the second half, VF2, this is going to equal, in this case, 2m2 over m1 plus m2 times VI1. Okay, we'll plug in our values here. We get 2 times 1.2 over 1.2 plus 3.6. This is multiplied by negative 7.2. And this gives us negative 3.6, which is equal to 3.6 meters per second west. There we go. Simple as that. So that was a special case where one of them wasn't moving at the start. We'll take a look at the second problem here. In a bumper car ride, bumper car 1 with that mass and speed hits bumper car 2 with this mass and speed. Calculate the final velocity of each bumper car immediately after the collision. Okay, we can't use our simple equation this time. We need to use the full thing, so we've got VF1 is equal to m1 minus m2 over m1 plus m2 times VI1 plus 2m2 over m1 plus m2 times VI2. Okay, now I could go ahead and fill out all those numbers for you. I don't really want to spend this time doing that. I'm just going to put a dot, dot, dot. We have all the numbers. You can fill them out, and the end result you get is negative 1.0 meters per second. And that gives us 1.0 meters per second west. On your sheet, by all means, fill out the numbers. I just don't want to spend the time in the video doing that. VF2, same idea. We have m2 minus m1 over m1 plus m2 times VI2 plus 2m1 over m1 plus m2 times VI1. Again, I'll do dot, 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 and it gives us a final value of 5.0 meters per second east. There we go. So the formula, it's long, it takes a lot of writing, but it's not that complicated to use. Hopefully you see the gist of it. If you don't, make sure to ask in class. Okay, we have two more special cases. We looked at the one where one of them wasn't moving. Let's look now at what would happen if the two masses are the same. So m1 equals m2. Well, in that case, our formula will change a bit. If m1 is equal to m2, I'm just going to call both of those m. So we have here that VF1 is equal to, so we've got, let's see, m1 minus m2, so we have m minus m over m1 plus m2, so m plus m, times VI1, plus 2m1, m2, so 2 times m over m1 plus m2, so m plus m, times VI2. Okay, and this gives us, well, you can see we get 0 for this whole first term, m minus m, plus 2m over 2m times VI2. So, hey, this is pretty interesting. It means VF1 is equal to VI2. If two objects collide in a head-on elastic collision, and they have the same mass, then the final of the first object becomes the initial of the second. It's like they just trade. We can do the same thing for the other one here. We have VF2 is equal to, well, you'll see that it's the same terms here. It's m minus m over m plus m times VI1, sorry, VI2 in this case, plus 2m over 2m times VI1. Okay, so again we get 0 for the first term plus VI1 for the second term, so you get that the final of the second is equal to the initial of the first. So that's a cool result. It means that they will just switch speeds. You can imagine if two billiard balls are approaching each other, they have different speeds, but they have the same mass. Okay? They're approaching each other. When they hit each other, it's almost as if they just passed straight through each other, because they're just going to transfer that energy so that the one on the right keeps going the same speed that the one on the left originally was, and vice versa. So it just sort of transfers, it goes through as if nothing changed. They just pass right through each other almost. Okay, number 2, special case. A light object plus a stationary and very heavy object. So we're talking about a light, so let's say a ping pong ball hitting something that's not moving and it's very, very heavy. It's like a ping pong ball hitting the wall, right? Technically the wall is going to move a bit, but almost nothing. So for this, we're going to pretend that m1 is just basically 0. Okay, and we'll put that into our equation. So if we're saying that m1 is a lot smaller than m2, and m1 is approaching 0. So we can use that in our equation. We've got m1 minus m2, so 0 minus m2 over m1 plus m2, so 0 plus m2 times vi1 plus 2 times, well, we don't even have the second term, right? Because vi2 does not exist. So vi2 is 0. So that's our whole equation there. You'll see that gives us, well, negative m2 over m2 times vi1. And so that just gives us that vf is equal to the negative vi1. So vi just keeps its same speed but changes directions. And let's see what happens to vf2. vf2 is equal to, well, remember our simplified equation here, it was 2m1, so 2 times 0, we're saying m1 has 0 mass, over m1 plus m2, so 0 plus m2, times vi1. Remember, we were using this simplified equation where vi2 is 0. The second object isn't moving. Okay, so this gives us a whole lot of 0. So that means that in the end, our final velocity here is equal to 0. So the stationary object doesn't move. The wall doesn't basically move, and the ping pong ball bounces back with the same speed that it came in at. And I'm just going to put these statements here, vf1, vf2, just so it's very clear that these are the results, and they're very interesting results, I think. Excellent. Okay, so we'll turn to the next page, and we're not applying those two special cases that we just found. You might see them on the homework. They're cool special cases, but we're going to go on to a new topic here. This is the conservation of mechanical energy. Okay, so we've talked about how in these cases kinetic energy is conserved, all this sort of thing. Well, if we have a spring involved in the problem, then maybe we can conserve all of this energy. And so this spring, so we're going to have our mechanical energy, which is kinetic and potential, all of this. Our mechanical energy, when these two objects collide, if there's a spring in between them, well, for a second, that's going to be converted into elastic energy, elastic potential energy. But then, so the spring will get compressed, and then it'll be pushed apart again, and it'll go back into mechanical energy, and as if sort of nothing ever happened. Okay, so we can convert for a second into that spring, and then convert it back into mechanical. And so our equation here, if we're saying that energy is conserved, and let's just use this first process. We just start with mechanical energy, and we convert into mechanical plus elastic. So we're giving some of our kinetic energy into elastic. So the equation we might use is something like this. We've got 1/2 m1 vi1 squared. So this is the kinetic energy at the start of the first object, plus 1/2 m2 vi2 squared. Okay, that's the total kinetic energy at the start. Well, it's going to add up to the total, the total kinetic energy at the end, 1/2 m1 vf1 squared, plus 1/2 m2 vf2 squared. But we're also going to have some elastic potential here, so 1/2 kx squared. So that's our situation. This is what we're going to work with. We're going to do a problem using that. And one interesting question we might want to ask is, what's the maximum compression? How much will the springs squeeze together before it starts going apart again? To do that, we need to say, when is it going to be at its max compression? And the answer is when the two carts have the same speed. Okay? When they have the same speed, it means that the spring is pushing the two of them equally. It means that one is not catching up to the other, one is not sort of moving at a different, so that when they both have the exact same velocity, I shouldn't say speed, when they both have the same velocity, that's when the spring has its max compression. Once it starts pushing them apart again, their velocities are going to change again. But when it's at its max compression, it's not pushing them apart or pulling them together, and so they're moving together, same velocity. So our equation for that, well, I guess first I'll say here that this happens when the final velocity of one is equal to the final velocity of the other. So that's when the spring isn't pushing them apart. Right, when the spring when it's at its max compression, it's not accelerating, there's no acceleration there. Or I shouldn't say there's no acceleration, but it's not pushing them apart. Okay, so that means we can simplify the equation above just a bit. 1/2 m1 vi1 squared plus, this part doesn't change. Okay, but now we have our final speed is the same for m1 and m2. So we have 1/2 m1 plus m2 times vf squared. We just have the one final speed. And we still have the elastic potential energy. Okay, so you see that simplifies things a bit. It's still a big equation, though. So we'll see one problem doing that. And we'll see how that works. So the problem says, Dynamics cart 1 has a mass of 1.8 kilograms and is moving with a velocity of 4 meters per second right along a frictionless track. Dynamics cart 2 has a mass of 2.2 kilograms and is moving at 6.0 meters per second left. The carts collide in a head-on elastic collision cushioned by a spring with spring constant K equals 8.0 times 10 to the 4 newtons per meter. Okay, we want to determine the compression of the spring in centimeters during the collision when cart 2 is moving at 4 meters per second left. Okay, so it's not at the maximum compression, it's just at some point where cart 2 is moving at that speed. So we're going to use our conservation of energy, and we're saying here, well, first we'll use our conservation of momentum to find out what the final speed of cart 1 is, right? To use conservation of energy, we need to know what the speed of both objects is. We know that what the final speed of cart 2 is. We can use our conservation of momentum to find the speed of cart 1. So m1 v1 plus m2 v2 is equal to, m1 vi1, m2 vi2 is equal to m1 vf1 plus m2 vf2. Okay, so we're saying that the momentum is conserved here, so we'll find out that we have vf1, because I want to find out what this final speed of vf, of the number 1 is. So it equals to m1 vi1 plus m2 vi2 minus m2 vf2 all over m1. That's just rearranging the above equation. And I can put in some numbers here. All of the numbers, 2.2 times negative 6.0 minus 2.2 times negative 4.0 all over 1.8. And this gives me 1.56 meters per second. Okay, good. So now I know how fast they're both moving. It means I can use my conservation of energy. And that looks like 1/2 m1 vi1 squared plus 1/2 m2 vi2 squared is equal to 1/2 m1 vf1 squared plus 1/2 m2 vf2 squared plus 1/2 kx. 1/2 kx squared, sorry. Good. Okay, it's a mouthful. That's a lot of math to be doing here. First off, we'll cross off all these 1/2s. We don't need them. Every single thing here is multiplied by 1/2, so they can all just disappear. Good. Now I want to solve for x. X is equal to the square root of, and I'm going to write all that out again, m1 vi1 squared plus m2 vi2 squared minus m1 vf1 squared minus m2 vf2 squared. All of that divided by k. That's our square root term. And I am not going to write in all those numbers. You are welcome to, but for the video, I'm just going to give us our final answer. 2.9 times 10 to the negative 2 meters, which is 2.9 centimeters. All that to say, the spring compresses 2.9 centimeters. But it's cool that we were able to find out that value, I think. Okay, now we want to calculate the maximum compression of the spring in centimeters. So what's the maximum it compresses? We use our simplified equation. We can actually have two simplified equations. So the speed in the end, Vf, is going to be the same for both objects, the velocity. So I can use that in my momentum. m1 vi1 plus m2 vi2 is equal to m1 plus m2 times Vf. So when the spring's at its max compression, they're moving at the same velocity. Good. So I can find what that max velocity is. Vf is equal to m1 vi1 plus m2 vi2 over m1 plus m2. And that is, again, I'll put in the numbers for this one. Let's do that. 1.8 times 4.0 plus 2.2 times negative 6.0 all over 1.8 plus 2.2. Good. So this gives us negative 1.5 meters per second. So they're going west at this point. Okay, now we use our x. We want to find x exactly the same as in the previous problem, where we just need to rearrange to solve for x. So I'm just going to borrow the equation that we have above for x equals the square root, that big term there. But I can simplify it because Vf1 and Vf2 are the same now. So I have my square root, and we have m1 vi1 squared plus m2 vi2 squared minus, now I have my m1 plus m2 times vf squared. All of that divided by k, and we'll take the square root. This is equal to, again, I'm not putting in the numbers, but we get 3.5 times 10 to the negative 2 meters, which is 3.5 centimeters. So that's the maximum that that spring will compress. Okay, this has been a long video, 25 minutes. I'm sorry, guys. I hope you enjoyed it, and we'll see you next time.